I am Dr. Karthika from the Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about isomeric transition and radiation and radioactive decay. Here we are going to discuss about the modes of radioactive decay and the decay of radioactivity. We are going to discuss about radioactivity and types, the modes of decay, alpha, beta and gamma decay. And decay of radioactivity, we have the activity, decay constant, exponential decay, half-life, methods for determining decay factors, image frame decay corrections. Okay, what do we mean by radioactivity? The radioactivity is the spontaneous disintegration of the atomic nuclei. An unstable nucleus, it releases energy to become more stable. It can occur in two ways. One is nuclear fission, another one is nuclear fusion. Okay, see this one, nuclear fission, the splitting of a nucleus into several smaller nuclei. This is what happens in nuclear power plants. See this animation, how cute is this? Okay, nuclear fusion, when two nuclei with low mass fuse to form one nucleus of larger mass, opposite of fission. The energy released by the sun and all the stars is due to fusion reactions in the core. Okay, then what do you mean by radioactive decay? It is the process in which an unstable atomic nucleus loses energy by emitting ionizing particles and the radiation transforming the parent nuclide atom into different atom called daughter nuclei. Here, see this one. The radioactive decay law, the rate at which a radioactive isotope disintegrates is defined by the following decay law. N by N naught, it is equal to e power minus lambda t, it is equal to 1 by 2 whole power t by th, where N is the number of atoms, N is the number of atoms of radioactive isotope at time of t of atoms at time 0. Here, lambda is a decay constant and N naught is number constant. Each isotope has different numbers and TH is half-life. Each isotope has different half-lives while emitting the radiation. Okay, and the modes of decay, we have alpha, beta, and in this alpha we have alpha and beta we have two types. For beta we have beta minus particle and beta plus particle. In gamma we have two forms. One is isomeric transition and another one is internal conversion. Okay, here see this animation for alpha decay. Here this shows the unstable nucleus which emits a new nucleus. By this we can get the alpha particle. Okay, here alpha, an atom decays into a new atom and emits an alpha particle, 2 protons and 2 neutrons, the nucleus of a helium atom. Here very heavy nuclei are often unstable as they contain too many protons. Typical alpha emitters have an atomic number lead 82. Alpha particles are emitted as they are extremely stable, they have high binding energy. And this is an example for alpha decay. We have when a nucleus undergoes alpha decay, the parent nucleus will suffer a decrease in atomic number Z of 2 and a decrease of 4 in mass number A. The daughter nucleus is now a different element. Here example we have consider the element X. It has the mass number A and the atomic number Z. It emits Y, A minus 4 and Z minus 2 plus alpha 42. Here alpha 42, it is called as helium 42. Okay, here we have an example of the form of decay occurs in uranium 238. Here the equation represents what occurs is uranium 238 92, it becomes thorium 234 90 by emitting the helium 42. Okay, and this shows the biological effects of alpha. Alpha particles are not penetrating, their only biological effects are to the surface of the skin with the production of radiation burns. Okay, next one is beta decay. See this one, how cute is this? Here we have unstable nucleus, it decayed into new nucleus, it emits beta particle. See this. This unstable nucleus, it decays and produces new nucleus and beta particle. Here Beta, an atom decay into new atom by changing a neutron into protons and electron. The fast moving high energy electron is called as a beta particle. Betas are physically the same as electrons but may be positively or negatively charged. Here betas are ejected from the nucleus, not from the electron orbitals. And all beta decays, the atomic number changes by 1 while the atomic mass is unchanged here. Okay, here we have two types in beta decays, beta minus and beta plus decay. Here we have the example N. The output is P plus proton and electron with some energy. Okay. Here we have an example. An example of this type of decays occurs in iodine 131 nucleus, which decays into xenon 131 with the emission of an electron. That is represented here. Okay, then see this one for beta minus decay. See this one. Here we have a parent and daughter, and we have the output is antineutrino. Also we have beta particle emission here. Okay, for beta plus decay, it occurs in proton-rich nuclides. A proton in the nucleus is transformed into a neutron and a positively charged electron. Here the positively charged electron or positron and a neutrino are ejected from the nucleus. That's it. Here we have some examples. Here the mass number remains the same and the atomic number decreases by 1. Also we have electron capture. Here, in this form of beta decay, an inner orbiting electron is attracted into the unstable nucleus where it combines with the proton to form a neutron. Okay, then biological effects of beta. We have the penetration of beta particles rather greater than alpha particles. The hazard is only if a beta emitter is ingested or inhaled. And this is gamma emission. See this one. Unstable nucleus. It emits new nucleus and gamma radiation. Here, in this gamma radiation, gamma after alpha or beta decay, the surplus energy is sometimes emitted. This is called gamma radiation and it has a very high frequency with shorter wavelength. The atom is not changed. In the gamma emission, we have two forms. One is isomeric transition and another one is internal conversion. Okay. In the isomeric transition, a nucleus in an excited state may reach its ground or unexcited state by the emission of gamma ray. Here we have an example. An example of this type of decay is that of tectanium 99 meter. And here we have internal conversion. In internal conversion, the excess energy of an excited nucleus given to an atomic electron, example of a K-shell electron. Here we have an example. See this example of this type of radioactive decay occurs in iron 55, which decays into manganese 55. The following capture of an electron, the reaction can be represented as iron 5526 plus electron. It produces manganese. And while talk about biological effects of gamma, the gamma radiation affects the internal organs of the body due to its high penetrating power. And the slide, it shows the properties of alpha, beta and gamma rays. That's it. Thank you all.